All right, so now we're going to be looking at, the uniform distribution kind of completely, because now with a uniform distribution, we're going to be able to calculate the theoretical population mean as well as the theoretical population standard deviation. Um, in the previous section, you saw that we had a probability density function, which is defined by this equation here, and A and B, where the maximum value in the PDF and the minimum value of the PDF. But now the mean of this function is equal to the minimum plus the maximum divided by 2. And the standard deviation is equal to the square root of the maximum minus the minimum squared divided by 12. Okay, and it's the square root of all of that. So we're going to apply this to some example problems, and we're going to look at some more examples of calculating area underneath the uniform distribution itself. Okay, this is all the same stuff I just talked about. So let's look at the first example here. So in this example, we're looking at the smiling times in seconds of an 8-week-old baby. So the following data is from 55 smiling times of one 8-week-old baby. So here it took 10.4 seconds for the baby to smile. Then here it took 19.6 seconds before a baby smiled, 18.8 seconds, 13.9, and so on. Now, if we take all of this data from this one baby and we calculate the sample mean and the sample standard deviation, these are the two values that we get. And notice that the minimum value here is 0.7, and the maximum value should be 22.8, which is right there. So this data is not sorted from smallest to largest. Now, if we were to take this data and create a histogram, this is what the histogram of this sample data would look like. Now, it doesn't appear, it looks like it has two modes, okay? But it doesn't seem to have, like any particular shape to it, other than maybe it does have a uniform distribution, something like that. So we're going to take the shape of the histogram and say that it's a uniform distribution. That means that the probability that a baby smiles in any number of seconds is going to be the same. The probability will be equal. The baby isn't going to smile, like more often in a short number of seconds versus a long number of seconds, for example. And from this, we're going to calculate an average number of seconds, a mean number of seconds that the baby smiles, and a standard deviation of time around that mean. Okay, so let's first look at the different components here. So in this histogram, for the purposes of this exercise, we're going to assume that the smiling times are uniform and that they're between 0 and 23 seconds. So here I noted that the minimum value is 0.7. We're going to start from 0 seconds here. And it went up to 22.8. We're going to go up to 23 to make things simple. Okay, and so what this means is that any smiling time between 0 and 23 seconds is equally likely. Okay, and it's equally likely because this is a uniform distribution. So part A is to state the values of A and B. Well, A is our minimum value, which is going to be 0, and B is going to be our maximum value, which is 23. So let's see here. A will be equal to 0, and B will be equal to 23. And, let me write this a little more formally here. So A is going to be the minimum of X, which was 0, and B is the maximum of X, which was 23. Okay, write the probability density function that models this sample. So the probability density function is this one. F of X, the function of X, is equal to 1 over B minus A. 1 over B minus A is going to be this value on the y-axis for the frequency, relative frequency, probability. Okay, so let's try and figure that out. So here we said that B was 23 and A is 0. So 23 minus 0 is 23. And 1 divided by 23, just using my calculator, is 0.0435. So I may use this fraction of 1 over 23 because that'll be the most accurate. I won't have to worry about my answers coming out weird by rounding a decimal. Okay, but this represents the probability density function. F of X is equal to 1 over 23. So now the next part is how close is the theoretical population mean and the standard deviation to the sample mean and the sample standard deviation. So what this is asking for is how close is the population mean to the sample mean? And how close is the population standard deviation to the sample standard deviation? Now, remember earlier, we could calculate the sample mean as 11.49 and the sample standard deviation was 6.23. What we want to know is we need to figure out what is the theoretical population mean of baby smiling times, and what's the theoretical standard deviation for baby smiling times. And that's where these two equations up above come in. So the theoretical mean, population mean, is going to be, what was that, A plus B divided by 2? There we go. And A is 0. B is 23. And that's going to be divided by 2. And then this will give us, what, 23 divided by 2, which is going to be 11.5. Now, how does this compare to the sample mean we calculated above? That was 11.49. These two are pretty darn close. All right, let's calculate population standard deviation versus the sample. So the theoretical population standard deviation is equal to square root, what was that, of b minus a squared divided by 12. So this will be the square root of b, which is 23, minus a, which was 0. That difference squared all over 12. Which is going to be equal to the square root of 23 squared over 12. So let's look at putting that into the calculator. So let's see how we could do that. So NumWorks, we'll do that first. We'll use the calculation app. So we want to take the square root of 23 squared divided by 12. I think what we're seeing here looks like what we're trying to do here. And let's look at, see if I can make that a little bit bigger. No, it's about as big as it's going to get. All right, so let's see if we can try and mimic this here on the Texas Instruments. So we're going to have the square root of, let's do 23 squared divided by 12. So it looks like, it's kind of easier to see how the NumWorks calculator formatted this, to say that this is going to match more exactly with what we're calculating. Here, it's kind of putting everything on a horizontal line, but this looks like it's the equivalent to what we got here. So let's go ahead and hit enter there and hit execute there. And it looks like we're getting the same answer. Okay. So we're getting approximately 6.64. So that's going to be equal to 6.64. That's the theoretical population standard deviation. Now, how does that compare to the sample standard deviation, which was 6.23? Well, these two values are pretty close. So what this demonstrates is that, from sample data like this, you can create a uniform distribution. And from that uniform distribution, you can calculate theoretical population means and theoretical population standard deviation means. And that will be a pretty good approximation of that. And that's going to be based off of the sample data that you collected. All right. So next is a think pair share that you'll want to try. It's very similar to this one. But let me go ahead and end this video here. Let me know if you have any questions.